Hello and welcome to this brief video about gravitational fields, potential and energy. So this is where we extend our knowledge about gravity and start thinking about what else it offers us. So we know about gravitational potential energy. We've learned about this before. We think, okay, this is mass times gravity times height, which is perfectly correct when we're thinking about this at the planet Earth scale. So we know that we increase the potential energy as the mass is raised above the Earth. And we know about work done in moving the mass between 2 points is positive when they're moving away from the Earth. And we recognize that that's because we have to overcome the force of weight, and force times distance gives an indication of the work done. And we also know that the work done is independent of the path taken between the 2 points. So it's actually all about the going up. If we go to the left, to the right, we wiggle around, then that doesn't make any difference. The work done is all about the distance traveled against the force. So that's our starting point. Now we're going to extend this a little bit because gravitational potential energy, as it happens, MGH works really effectively if we're thinking about something close to the surface of planet Earth. But we also recognize that actually it's a little bit more complicated as we go further out. So there, potential energy is going to be about overcoming the force of gravity. And we recognize this force of gravity is calculated by gmm divided by r squared, and then multiplied by that distance away, that r. So it gives us the gravitational potential energy is minus g, gravitational constant, the mass of the, in this case planet Earth, the mass of the body, and r, which is the distance from the center of planet Earth. Although do note there, this is only really valid when we're going from the surface. So little r needs to be bigger than the radius of the Earth. So gravitational potential is given by this formula we've just explained. So gravitational potential, remember, incorporates as the how much potential energy per kilogram. So that little m gets cancelled out. We recognize it has to be a distance r from the center of the Earth, providing that r is greater than the radius of the Earth. And the negative sign allows us for the fact that all potentials are negative as they have to increase to zero. So that's just a consistency feature which we've got there. So gravitational potential difference is a measure of the amount of work a particle has to be done on, or done on a particle, between 2 points in a gravitational field. And so this is joules per kilogram. Okay. Notice that per kilogram is really, really important there. The work done is independent of the path taken, exactly as we said before. It's about the two distinct points, and we work out what the gravitational potential energy is in both those places, and we work out that potential difference per kilogram. So, things to note. Okay, the gravitational field strength is the negative potential gradient. So, what does that really mean? Okay, so gravitational field strength is gravitational constant multiplied by the mass divided by r squared. Okay, so that gives us the field strength at any point. Now, the gravitational potential is the field strength, so the force multiplied by the distance traveled. So therefore, our gravitational potential is minus g multiplied by mass divided by r. Okay. Now we notice here the gravitational field strength. We'll have these arrows going down towards the center of the Earth. And the gravitational potential will have these lines where we see that the gravitational potential is the same at different locations. Now, this is the most important formula. This is the linking formula, okay? Is to recognize that G is actually the gradient, or the potential gradient, of the change in gravitational potential divided by the change in R. Okay? So that's a really important link between gravitational field strength and gravitational potential. You're going to use that formula quite a bit. Note here that we have these things called equipotential field lines. And what this happens is there are ways to display points in space that have the same potential. I've got a couple of examples here. Now, they're always normal to the field lines, so they're always at 90 degrees to the field lines. And the other thing to think about here is if you're traveling along an equipotential field line, you're not actually doing any work because you're not working against the force which is causing that. My final note here is gravitational potential due to more than one mass, and this comes up in questions as well. Now, gravitational potential is a scalar property, so it's just a number. So that means at a point, let's say between the Earth and the Moon, there's a point when the gravitational potential is all sum and the equal is zero. And this is the point where the force of attraction are equal to each other. So basically they cancel out. So that's another feature that often comes up in questions, and that's something to work through. And often we'll do simultaneous equations to try and work out where that point R is. You'll be practicing that in the future. Okay, thank you for that. Good day.